Yeah, welcome back to the study club. This week we'll be reviewing the Sumcheck protocol and some applications of it, in particular applied to sharp SAT and a question of graph equivalence. What was the exact word? Graph isomorphism, that was it. Yeah, so we'll be talking about sharp SAT and graph isomorphism sort of leading up to next week, when we'll sort of be hitting one of the crown jewels of this section, which is the GKR protocol, which uses Sumcheck in a slightly different way from the sharp SAT circuit example, but also in a circuit to prove that the prover has a witness, or has computed a witness to some input that goes through a circuit. So yeah, morning, Justin.
Morning. Yeah. The graph thing today is triangle counting. Yeah, there are too many graph problems. The isomorphism comes up in the zero knowledge discussion later. So remind me, Thor, are we diving into the book? I forgot on if this is like an implementation week and what the current plan is on such weeks.
Yeah. So my initial intuition was that we should alternate implementation weeks and book reading weeks, but I think that a slight modification might be a little bit better, where if we can hit something that's sort of more like an example that people can follow along with, possibly having read the section or possibly having not, but keeping the section reasonably short or high level. I think that would probably be the way to sort of balance implementation weeks with just a little bit of reading. And so that's sort of the thought behind reading section 4.2 and 4.3, which I think is a total of 4 pages, about 2 examples of using Sumcheck protocol. So yeah, I think that was that is the thought behind talking about stuff in this order. And I'm sort of just winging it here. So if you have feedback about the pace going too quickly, or you prefer a different format, people in the audience can yell at me and they do it different. So
okay, sounds good to me. So I should just launch into my summary of this week's reading, and then we can have a discussion.
Yeah, that sounds good.
Okay, cool. Yeah. So sort of despite the reading being short, it's a really important, there's a lot sort of to discuss, because last week the reading covered the Sumcheck protocol, which is like the key hammer when designing efficient interactive proof systems. And this week, we read about the first 2 applications of that hammer. And so while, the applications sort of in hindsight are clean and fit in 4 pages to talk about both of them, there's really a lot going on, because the Sumcheck protocol is a really remarkable hammer. But when you first see the hammer, it's not obvious that anything is a nail. But sort of once you see some examples, I hope it becomes clear that, in fact, almost everything is a nail. And if that's not clear after this week, it should become more believable after next week when we see the GKR protocol, because that protocol is for what we call like a universal problem. So circuit evaluation. So like you can take an arbitrary computer program and turn it into a circuit evaluation problem. So once you give an efficient interactive proof for circuit evaluation, you can, in principle, give an interactive proof for any efficiently computable problem. Like take your fast computer program, turn it into a circuit, apply the interactive proof for circuit evaluation. Okay, so yeah, today the 2 applications that you should have read about, one was for a problem called sharp SAT, the other for counting triangles in a graph. So the name of the game when, trying to use the Sumcheck protocol to give an interactive proof for a problem is to go through the following sort of design process. So what you're going to need to do is you're going to need to identify a multivariate polynomial G. So let's say the number of variables is V. And, for each problem, like V is going to differ, like how many variables you're going to need to achieve the following. And we're going to want G to satisfy 3 properties. And these properties can be a little bit in tension with each other, but it turns out, as the examples, today show, you often can sort of satisfy all 3 properties at once. So the first property is that the quantity the verifier wants to learn, like the problem we want to solve, has to equal the sum of G's evaluations over 0, 1 to the V. So that is over the Boolean hypercube. And that's because the problem the Sumcheck protocol solves is exactly forcing the prover to correctly sum up the polynomial's evaluations over 0, 1 to the B, right? So you want like that sum to be exactly what the verifier wants to learn, the answer to the problem. Then we need, the second property is that the polynomial G has to be low degree in each variable, because that's what's going to keep the proof short. And then the last property is that the verifier needs to be able to evaluate G quickly at a randomly chosen point in field to the V. That's because the verifier's very final check in the Sumcheck protocol entails evaluating G at just one point. So we need the verifier to be able to do that quickly if we want the verifier to run quickly. Yeah, so these are like three kind of bizarre abstract properties we need that the first time you see them, you probably are like, well, that's weird. Like what problems could that possibly capture? Very artificial, summing up some polynomials evaluations over the Boolean hypercube. But it turns out, again, to be very powerful. So the first example is that for SharpSat, the problem is as follows. So the prover and verifier kind of agree on what's called a Boolean formula. So I think the book denotes that formula by phi. So this is, and it calls the size of the formula S. So with the Boolean formula, the situation is there are n variables that are fed as input to the formula phi, and these variables take true false values. Right. And then what phi does is kind of evaluates a bunch of and or not operate. It applies and or not operations repeatedly, first to the inputs, and then, it takes ends and ors of those gates, and then ends and ors of those gates, and so on and so forth until it computes just a single output value, which itself is true or false. And yeah, that's what a Boolean formula is. And, we always sort of by convention associate the number 0 with false and the number 1 with true. So we can think of the formula as mapping n bits, so 0, 1 to the n to 0, 1, where 0 is false and 1 is true. Okay. So that is sort of the setup for SharpSat is, the prover and verifier agree on this formula phi of size S over n variables. And the verifier wants to know how many satisfying assignments the formula has. So that is out of the 2 to the n possible, true false assignments to the n input variables, how many of them cause the formula to evaluate to true? Okay. So this is believed to be a totally intractable problem. Okay. The fastest known algorithms for this problem are believed to basically be brute force. So that means the algorithm more or less is going to have to iterate over every one of the 2 to the n possible, Boolean valued inputs. Yep. Question? No question? Okay, sorry. No, and I'm not showing a screen. I'm just talking. So I hope that's what I'm saying is followable. But I am hoping that I'm following the notation in this section, although I don't have it in front of me at the moment. Okay, so yeah, please interrupt if you have questions. Yeah, the fastest known algorithms for this problem are believed to just sort of iterate over every one of the 2 to the n possible inputs to the formula and sort of just evaluate the formula gate by gate on that input. And count, how many of them cause the formula to evaluate to true. So the runtime of that brute force algorithm is formula size S times 2 to the n, because for each of the 2 to the n inputs, we're spending time S to evaluate the formula, see if it's true, spits out true or false. And if it's true, we just, add 1 to the running sum. Okay, so, the readings show that using the Sumcheck protocol, we can give an interactive proof for the problem where the verifier runs in time. I think it's order S times n. So that's within a factor of n of optimal for the verifier, because the verifier has to at least read a description of the formula. So if the formula has, size S, then just reading a description of that formula is going to take time S. So the verifier here is pretty close to the fastest possible time we could hope for, and just sort of understanding what formula it's even looking to count the number of satisfying assignments to. And the prover in the protocol runs in time, I think it's S squared times 2 to the n. So that's within a factor S of optimal, right? Because I said, it's widely believed that the fastest known algorithm is basically brute force, which takes time S times 2 to the n. Now we don't know that for sure. That would, entail showing that P doesn't equal NP or whatever. So we're very far from showing that for sure. But that's the prevailing belief, is that this is a totally intractable problem. Brute force algorithms are pretty close to the best. So yeah, this is up to a factor of S for the prover and N for the verifier. These runtimes are the best we can hope for. So you might think, oh, this is maybe practical. I want to be clear. This protocol, the SharpSat protocol, not meant to be practical. And there are 2 reasons for this. I mean, one is a factor S overhead for the prover and a factor N overhead for the verifier compared to the best we can hope for. In practice is going to be bad. In practice, we really care about those factors. But the more fundamental reason is no one can even solve SharpSat in the real world for large scale, worst case instances, right? Because this brute force algorithm that takes time S times 2 to the n, even if n is I don't know, 60 or 70 or something, that's going to be beyond the reach of existing computers to brute force this problem. So, this is not meant to be a problem that people are going, take this protocol and like deploy it tomorrow, but it is a stark demonstration of the power of Sumcheck because, we're sort of fits on a page. And we're getting like, a nearly optimal verifier time and a nearly optimal prover time. In particular, the verifier runs in polynomial time if the formula, is polynomial size in n, when the problem itself is believed to be totally intractable. So without a prover, the verifier would not be able to solve the problem in polynomial time. Okay, so with all of that context out of the way, here's how the interactive proof works. So the verifier...
Could I jump in real quick and ask a question?
Yeah.
You mentioned in section 4.3 a property called doubly efficient, where the time to solve the problem runs in O of t time and O of s space, that the prover runs in O of t time and O of s space, and the verifier runs in linear time, and you don't make a remark about space. You didn't mention Sumcheck when you were talking about doubly efficient algorithms, but I was curious, since you brought it up in section 4.3, if Sumcheck qualifies as a doubly efficient algorithm, or if it just sort of depends on how expensive it is for the verifier to evaluate G and how expensive it is for the prover to compute the circuit.
Yeah, great. Let me just pull up that section to see what I wrote, just to make sure that I don't say something that slightly differs from what I meant when I wrote it. So I said we want the prover to run in polynomial time and the verifier to run in linear time. Yeah, okay. That's what I thought what I wrote. Okay, so I would say, so this SharpSat protocol, this interactive proof of SharpSat is not doubly efficient for two reasons. One is the verifier in it does not run in time linear in the size of the input. Right. And that's because, so we're thinking here, I guess, of the input to the verifier as being a description of the formula phi, which has size s. So like, just writing down phi is going to take at least like s bits or whatever. So the input size for the verifier is like s here, the size of the formula. And so to qualify as doubly efficient, at a minute, the verifier would have to run in time linear in s. And in this protocol, the verifier runs in time order s times n. So that's polynomial time, but not linear time for the verifier. So that's one reason this isn't doubly efficient. But the even more important reason this isn't doubly efficient is because the prover doesn't run in polynomial time. Now, we can't really hope for the prover to run in polynomial time because it's very widely believed that there simply is no polynomial time algorithm for this problem, even if you don't worry about, proving correctness of the answer. So for both of those reasons, the SharpSat protocol is not doubly efficient, but the counting triangles protocol that, we'll get to next is doubly. And your question was, is the Sumcheck protocol considered doubly efficient? And I think the answer to that has to be, it depends on the application. The Sumcheck protocol is a key tool to design like the most efficient possible interactive proofs. But if you're using it to solve an intractable problem like SharpSat, you're not going to get a doubly efficient protocol out just because, again, even you could hope for the verifier to run in time linear in the size of the input, but you can't, if the problem's intractable, you cannot hope for the prover to run in polynomial time just because by definition of intractability, like you can't even solve the problem in polynomial time. But if you apply it if you use the Sumcheck protocol, to solve a tractable problem like counting triangles where there is a polynomial time algorithm known, then you often do get a doubly efficient interactive proof out of it.
Tractable. When you say tractable, you mean that it can be solved in polynomial time, right?
Yeah, that's exactly what I mean. So basically, I guess I would say the Sumcheck protocol tends to yield doubly efficient interactive proofs when applied to problems in P, meaning solvable in polynomial time, and cannot possibly yield a doubly efficient interactive proof when applied to a problem that's not in P, just because the prover can't even solve the problem with no guarantee of correctness in polynomial time. That's the rule of thumb, I guess.
Makes sense.
Any other questions?
So about footnote 37. So I don't know much about circuits, but just want to check my understanding. So the OR circuit has fan out rate, right? And NOT has fan out too.
Right. So yeah. So the footnote numbering is probably different in my version because I keep posting little updates to the book. But I'm guessing you're asking about the difference between a formula and a circuit is that gates in a circuit may have fan out more than one, while gates in a formula have fan out exactly one. Yeah. So what you said is correct. So another way to sort of define a formula is the wiring of the formula is required to be a binary tree. So that means every gate in the circuit. So it gets a little pedantic, but let's just assume for simplicity there are no NOT gates. Okay, you can work NOT gates in just by negating some of the inputs. Just you don't need NOT gates like other than right at the input level. So yeah, you can define a formula by insisting that the wiring be a binary tree, which means like every gate in the circuit has fan in 2 and fan out 1, except for the output gate, which has fan in 0. And then the inputs to the binary tree are just like the n inputs to the formula x, but you might have to repeat the same variable many times if there are many gates that sort of want to be many ANDs and OR gates that want to be fed that input. Yeah, and so conceptually speaking, the difference between a formula and a circuit is that a circuit can kind of reuse computation, so it can like compute a value somewhere inside it and then like feed that value to many different additional gates downstream of it. Whereas with the formula, it's like it can never reuse a value because of this fan out 1 requirement. So if it sort of wants to use the same value like 50 times, it has to compute that value from scratch 50 times. Since it can never sort of send that value onwards to like 50 different gates, it can only, send it to every time it computes it, it can only send that value onward to 1 gate. Did that make sense?
Yes, it clears up things up a little bit, but though in the text, it says the number of gates in the arithmetic circuit is at most 3s. Is it because of OR? I mean...
Yes, that's exactly right. Yeah. So, jumping ahead to the protocol, which, I mean, it's not everyone read it. So it's, the way the protocol works is the way it gets a polynomial to apply Sumcheck to is it takes the formula, which consists of AND OR NOT gates, right? And it turns it into an arithmetic circuit where the gates compute addition multiplication over a finite field in such a way that like the arithmetic circuit is guaranteed to compute a polynomial that extends the formula, meaning, if you evaluate the polynomial computed by the arithmetic circuit at any Boolean valued input, it spits out the same, 0, 1 value that the formula would. And yeah, so you're exactly right. So that transformation from formula to circuit goes gate by gate through the formula and replaces each AND OR and NOT gate with basically like the 2 variable multilinear extension, or for NOT, it's actually 1 variable, the multilinear extension of that gate operation. And so AND gates just turn into multiplication because like AND maps 1, 1 to 1 and anything else to 0, 0, 1 goes to 0, 1, 0 goes to 0, 0, 0 goes to 0. So that the multiplication extent does the same thing. 1 times 1 is 1, but 0 times anything else is 0. And similarly, a NOT gate, it just kind of turns into 1 minus, right? So like, 1 minus X maps 0 to 1 and 1 to 0, which is exactly what knotting a Boolean value does. So the only one of those 3 gates and or not that turns into more than one arithmetic operation to compute the little multilinear extension of it is OR. So you understand exactly the multilinear extension of OR requires, what is it? It's OR of x1 comma x2 equals x1 plus x2 minus x1 times x2. You can just kind of check the 4 values all do the right thing. 0, 0, 0, 1, 1, 0, 1, 1. So that requires 3 gates in the arithmetic circuit. And that's where the 3 is coming from. So that's just me repeating exactly what you said in 50 extra sentences. So yeah, that's why I wrote 3s instead of s is because if the whole formula was OR gates, then the resulting arithmetic circuit would be 3 times as big in terms of the number of gates as the formula.
Can you explain a bit about footnote 38? It basically, I don't know if you have it or not.
Is it about the claim that the polynomial computed by the resulting arithmetic circuit has degree at most, like total degree at most s or whatever? Is that the one?
Yeah, like 2s. And in the footnote, it explains an inductive proof for it, but I don't quite understand it.
Yeah. Sure. Okay. So I guess things might be easier if I had like sort of defined a formula to just be a binary tree, which maybe I should go back, like the wiring has to be a binary tree. But yeah, I'll do it sort of the conceptual way. So imagine first that the formula is just a single AND gate. So there are 2 input variables, x1, x2, right? And the formula computes x1 times x2. Sorry, and the formula computes x1 and x2. right? So the resulting arithmetic circuit will just be x1 times x2, right? So the total degree of that polynomial is 2, right? X1 times x2 is a polynomial. It's multilinear. It has total degree 2, right? Because the sum of the degrees in the one monomial is 2. X1 has degree 1 and x2 has degree 1 in the same monomial. That's total degree 2. Okay. Now imagine, I guess for simplicity, that the formula, has this is where induction is sort of going to come in, has depth 2 instead of 1. So if it's just a single end gate, that's a depth 1 formula that just, has one end gate. Now, so let's say it's all end gates. So it's, what we have now is an end, the output gate's an end, and then that's fed 2 ends. So basically the formula is computing the end of 4 variables instead of 2 now, x1, x2, x3, x4. Okay. So, the way the inductive proof works, and that, in the footnote you're asking about, is it's like you can assume by way of induction that the 2 end gates, at that, just above the inputs, like each of those computes the formula of depth 1, right? So like by induction, by the base case that I just explained, each of those gates sort of get arithmetized into sort of a polynomial, like an arithmetic circuit computing a polynomial of total degree 2, right? And then the output end gate now, there's one extra layer than the previous case. The output end gate just, gets arithmetized into the product of, the arithmetizations of the 2 end gates, that are feeding into it. So what comes out now, of this depth 2 circuit over 4 inputs, depth 2 formula over 4 inputs, is a polynomial whose total degree, right? It's, the polynomial is just the product of the 2 polynomials feeding into the output gate. So, if you product 2 polynomials of total degree 2, you get a polynomial of total degree at most 4, right? And so this is the inductive proof, is like, every time you like add another layer to the formula, you sort of inductively handle, like assume you've already proved a degree bound for the arithmetizations of, like the sub formulas that feed into the output gate. And then the output gate gets sort of arithmetized itself into a total degree polynomial, a total degree 2 polynomial of its inputs, right? So you just combine the inductive hypothesis that says, each of those inputs has total degree at most, size over 2, you product those 2, degree size over 2 things together, and you get something a total degree at most size out. Did that make sense? Yeah. I kind of babbled really badly.
Yeah, I think I kind of understand it like intuitively.
Yeah. Okay. I guess that means I didn't totally fail. I guess I would suggest just some examples. I'm trying to remember. I don't remember if I had that, some exercises that basically said, work through these examples. But yeah, I think if you just write down some formulas, of like size 8, depth 3 or something, and then, turn them into the arithmetic circuit that computes the extension polynomial as described in the book, and you like look at the degree of that polynomial, you will very quickly sort of understand what's going on if it's not already clear.
Can I understand it as like if I treat every gate as an AND gate, so it will just at most be 2s?
Yeah, I think that's right. So nothing like really fundamentally changes if it's not all end gates, right? Like what's really important is that the arithmetic circuit that the formula gets turned into, all that's important is that each gate and or not is getting sort of replaced with a total degree 2 polynomial in the arithmetic circuit, right? So n gets replaced with x and y gets turned into x times y, that's total degree 2. Not x gets turned into 1 minus x, that's actually total degree 1. That's even better. That doesn't change the degree at all, it turns out. And then or of xy gets turned into x plus y minus x times y, also total degree 2. So that's like this degree bound claim that you're asking about, this footnote sketch, the inductive proof. The only property it's exploiting of like, and or not in their transformations is that each one of these is getting turned into like a little sub-circuit in the arithmetic circuit that computes a total degree 2 function. So nothing really changes if you just think about the formula of size, n, let's call it S, that just is all end gates. right? And then the resulting circuit, that arithmetic circuit that comes out, is like super simple. It's literally just the product of all the inputs. And so for that, you can directly see, that. So it's just like every AND gate just gets turned into a multiplication gate in the arithmetic circuit. And that's how to see that, the formula with S AND gates got turned into an arithmetic circuit computing a total degree S function, right? Because in that case, it's literally just product out all S inputs to the resulting arithmetic circuit.
Oh, okay.
Any other questions? Okay, so I see there's a question in the chat. Do you think using the same notation of B1, BV and the Sumcheck proof is better? Sorry, I see. I think this question is referring to when introducing the problem of sharp-sat, should the number of variables be V instead of N? Yeah, I mean, this is tricky. Was that the question?
No, actually, I was referring to this proof of Sumcheck protocol. So like in the problem statement, so it's basically non-issue. It's not a mathematical issue, but just saying that in this problem statement, you are using the notations B1 to BV to denote to denote the set of all the binary strings. And then in the proof, you switch to X1 to X3. So I was just saying, is there any specific reason to change B1, the notation to X1's Xi's, rather than staying with BI's?
Yeah, okay. No, that's probably actually just an oversight. Yeah. No, there's not a good reason for that. So I might have had in my head, trying to distinguish between formal variables versus, 0, 1 vectors that the formal variables kind of get fixed to over the course of the protocol, but then I wasn't consistent about it or something. So yeah, there's not a good reason. I'll go back and revisit that. Thanks. Okay. Anything else right now? Cool. Okay. So yeah, great questions. Hopefully my babbling has clarified some of them. Yeah. So I guess just to finish very briefly summarizing, the sharp-sat protocol, but we sort of already talked about details of it. So it's a little redundant, but essentially, yeah, the verifier, in designing the protocol needs to identify some polynomial G, right? And remember, there are 3 properties G needs to satisfy. Like the first is that the value the verifier desires to learn is the sum of G's evaluations over all, 2 Boolean inputs, right? The second is that G have low degree in each variable, because that sort of determines the length of the proof. And the third is that the verifier can evaluate G quickly at a single random point, right? So this G is obtained in the sharp-sat protocol by, viewing the formula phi as a function mapping, 0, 1 to the n to 0, 1, where again, we're thinking of 0 as kind of false and 1 as true, and taking some extension polynomial of that function. And that then sharp-sat, summing up the number of satisfying assignments of phi is equivalent to summing up G's evaluations, by the extension property. And yeah, the G is obtained by sort of taking the formula phi and sort of going through it gate by and replacing each and or not gate with a little, 2-variant minor polynomial that extends that gate. And that turns it into an arithmetic circuit, which computes some polynomial G. And, again, we've sort of talked in detail about why the degree of the polynomial computed by that circuit is not too big. And sort of because the circuit was designed to sort of agree gate by gate with the formula, that's how you know that the polynomial G computed by the circuit extends the formula phi. Yeah, and that's where the prover and verifier just apply the Sumcheck protocol to G. And when the verifier goes to evaluate G at a random point, it amounts to just evaluating the arithmetic circuit at that desired point, gate by gate. And since they're at most 3 times, formula size many gates in the arithmetic circuit, that's the amount of time it takes, the number of addition multiplication over the field operations, for the verifier to evaluate the extension polynomial at a random point. Okay, so there's a question, would NP equals P if we find a polynomial verifiable IP for an NP complete language? So, okay, firstly, let me address this question. So NP is a subset of IP, right? NP captures non-interactive proof systems, right? An NP proof is a proof system where the proof is a static string, that the prover just writes down a string. And the verifier, there's 0 probability that the verifier makes a mistake in terms of accepting a proof of a false statement. So in fact, we do have polynomial time verifiable interactive proofs for NP complete languages, and they're not even interactive. The definition of NP sort of says there's a polynomial time verifier for the language with a static proof. Now, this does run into, we had a long discussion when we were reading chapter 2 or 3 about the difference between interactive proofs for functions versus languages, where for languages, it's not required that there be convincing proofs of non-membership in the language, because you're thinking then of, inputs in the language as like true statements and inputs not in the language as false statements. And so it sort of makes sense when talking about interactive proof systems for languages to only require that true statements have convincing proofs and not require that false statements have like convincing proofs of their falseness. So that you do run into a little bit of subtleties there. So if you're asking about consequences of having a interactive proof for both an NP complete language and the complement of that language, that is requiring convincing proofs of membership in the language and non-membership, then there can be some interesting consequences if the interactive proof is constantly many rounds. But in fact, it's known that actually any problem in P space, which is a huge complexity class believed to be vastly bigger than NP, it's known that any problem in P space has an interactive proof with a polynomial time verifier. Okay, so this is a famous result that's actually discussed briefly in today's reading, which I won't say much more about until we get through the counting triangles thing, if we have time. But yeah, basically so to sum up my babbling here, interactive proofs with polynomial time verifiers are extremely powerful. They're capable of solving any problem in P space. So that means a problem solvable with at most n to the 50 space, which, such an algorithm using n to the 50 space could take time like 2 to the n to the 50. And still there would be an interactive proof for that problem with the polynomial time verifier. Yeah, so just the one sentence answer is actually there are interactive proofs with polynomial time verifiers for problems even way beyond NP complete in terms of hardness. But of course, for those those interactive proofs are not doubly efficient, because the prover is not going to run in polynomial time. Even just to solve a P-space complete problem is way beyond, is believed to be way beyond polynomial time computation. Okay, did that make sense? Does anyone have follow-up questions about that discussion?
I have a lot of questions about IP equals P space. So, but I don't want to take too much time here. So should I ask the questions here or just post them in the chat later?
I would say let's do this. Let me briefly run through the counting triangles protocol. I'll do it quickly, and then we'll just see how things go. I'm also happy to stick around after the hour, or we could do it in the chat, and then anyone else can read it, even if they're not here today. So anything's fine with me. Does that sound good? I'll run through counting triangles, and then we'll go from there.
Okay. Thanks.
Great. Yeah. So, again, to repeat, like SharpSat is a totally intractable problem. No one can solve that in the real world for worst case inputs unless, the problem instances are super tiny. Counting triangles is a problem that people actually do solve in the real world, and has applications in computational biology and social network analysis and stuff. Okay. In this problem, the input is a graph, which is just a collection of vertices and edges connecting them. So like an edge just is like, you can view the vertices as dots, and an edge just connects two vertices like with a line. And a triangle is a triple of vertices, any two of which are connected by an edge. So it's like on Facebook, if Alice is friends with Bob, who's friends with Charlie, who's also friends with Alice, so they're all friends with each other, that's a triangle. So the book gives an interactive proof for this problem, whereby the prover runs in time like n cubed, where n is the number of vertices in the graph, and the verifier runs in linear time. So the verifier is up to a constant factor, like as fast as you could possibly hope for, and this is what's required by the notion of doubly efficient interactive proofs. And the prover's runtime is as fast as the naive triangle counting algorithm that just like brute forces the problem by iterating over every triple of vertices in the graph and checking to see if they form a triangle. Later in the chapter, there is a more efficient for the prover interactive proof given, but we're going to skip over that. But of course, you're welcome to read it. I think it's like gives you more practice with the Sumcheck protocol, but it's definitely not key on a first reading of this book to, go and find the more refined, complicated interactive proof for this problem. Okay, so the interactive proof for this problem that we covered today identifies a polynomial over 3 log n variables of degree 2 in each variable, such that the number of triangles in the graph equals the sum of this polynomial's evaluations over all Boolean inputs. And note there are NQ Boolean inputs, of length 3 log n. Right, so this polynomial has 3 log n variables, And so 2 to the 3 log n is n cubed. So it turns out, though, that the verifier can evaluate this polynomial at a random point in time order n, right? So it's can evaluate the polynomial at a random point faster than it would be required to, compute the sum on her own. Obviously, if she could compute the sum on her own, then there's no point in resorting to a prover. And I think the key point that I want to just convey here, because this is a perspective that is taken throughout the, many, many snarks in the literature, and it takes some getting used to, is as follows. Where do these 3 log n variables of this polynomial G come from? So one associates each of the n vertices in the input graph with a log n bit binary label. And then the verifier and prover, the protocol designer, views the input, which we're thinking of as the adjacency matrix of this graph, with rows indexed by nodes and columns indexed by nodes. And, Aij is 1 if and only if the 2 nodes are connected by an edge. We then view the adjacency matrix of the graph not as a bit vector of length n squared, or, a matrix of with n by n entry, n squared entries, but instead as a function mapping 2 log n bits to 0, 1, right? That is this function. We're interpreting the input to the problem as a function in which the input to the function is the index of one of the input bits. And the function, outputs the input bit corresponding to that index. So in the context of this graph problem, right, the 2 log n bits fed to this function specify or interpreted as, the binary labels of 2 vertices from this n vertex graph. And this function spits out 1, if and only if those 2 vertices are connected by an edge in the graph. And so it's a weird perspective. Most people are going to think of the inputs to the problem as a vector of length n or an n by n matrix or something. But the interactive proof used the input as a function with domain, the Boolean hypercube, in this case, 0, 1 to the 2 log n. The reason this is done is because once you view the input as a function with domain equal to the Boolean hypercube, that function has a unique multilinear extension, which we talked about, I guess, 2 weeks ago. Okay, so the polynomial G that we apply the Sumcheck protocol to in the interactive proof is defined in terms of that multilinear extension. So it's what G of x, y, z, where each of x, y, and z is log n variables. How it's defined is G is just the kind of the product of 3 copies of this multilinear extension function, where the first copy is fed x comma y, the second is fed y comma z, and the third is fed x comma z, right? And the reason that definition is the way it is to ensure that this polynomial G, which has degree 2 in each of its variables, extends the function we really want to sum up, which takes as input, 3 vertex labels, x, y, z, and spits out 1 if and only if they form a triangle, right? So that's what ensures that summing up the polynomial's evaluations over the Boolean hypercube, 0, 1 to the 3 log n, is equivalent to, iterating over all possible, triples of vertices in the graph, and, including a 1 in the sum if and only if they form a triangle. And then, this polynomial has the extra property that's, we require, which is that evaluating this polynomial G at a random point, in field to the 3 log n can be done by the verifier in linear time, because, to evaluate G at R, it's enough to evaluate, the multilinear extension of the input at 3 points, R1, R2, R2, R3, R1, R3, right? And then we talked about algorithms 2 weeks ago for doing exactly that efficiently. So given a function defined over domain Boolean hypercube specified by a list of its values, how can you evaluate the multilinear extension of that function in time linear in, its description? That's exactly what the verifier here needs to do. It needs to do it 3 times, once for input R1, R2, once for R2, R3, once for R1, R3. Okay, so thank you for letting me ramble about that. Let's see if there are any questions. But yeah, it's that perspective, I'd say, that's viewing this, input, in this case, it's length n squared, just that's the notation of graph problems. N squared is the input length. Viewing it not as a vector of length n squared or as an n by n matrix, but instead as a function on 2 log n bits. That's where when you're trying to apply the Sumcheck protocol in this doubly efficient interactive proofs, that's what always happens is the polynomial you apply Sumcheck to is derived from the multilinear extension of the input. For that to even make sense, you have to interpret the input as a function on like log n bits. Okay. Any questions?
So in figure 4.3, y values in the matrix is like these numbers, not 1 and 0.
Yeah, good. So that is just for generality. It actually having these non-zero one valued entries of a matrix actually does capture sort of counting triangles and weighted graphs, but that's not discussed at all in the chapter. So that's confusing, admittedly. But yeah, if your edges in your graph have weights and the weight of a triangle is like the product of the weights of the three edges in the triangle, then your input would be, a matrix with non-zero one entries, and everything would just work as written anyway. But yeah, this figure is done sort of in more generality where the matrix, doesn't just have 0-1 entries. I think I made that decision because I didn't want people to sort of get confused between the domain and range, right? Because the domain of this function is, 0-1 to the 2 log n. And so like the inputs to this function, like f sub a in this figure are all, the 16-bit vectors 0, up to 111. And I didn't want people to sort of think that 0, was in any way associated with like output 0 or output 1. They should be thought of as like different. So I think that was my thinking as I put this figure in. And I think what I'll do is I'll leave it, but I'll put in an extra clarification, like in the problem define, counting triangles defined in this section, the entries of the matrix themselves will be always 0-1 because it's an unweighted graph. Does that answer make sense? Any other questions? Do we want to talk about IP equals P space? And, if people have additional questions, feel free to jump in or put them in the chat.
Before we jump into IP equals P space, you mentioned that P space is believed to be a vastly larger class than NP. With sort of like a clarification, I'm trying to remember the exact difference between NP, NP hard, and NP complete. In my notes, I have that NP hard problems are not necessarily decision problems, whereas NP complete problems are decision problems. And that an NP hard problem is a problem is NP hard if and only if there exists an NP complete problem that can be reduced into it in polynomial time. Is NP hard the same as NP, or is NP hard, and NP complete three different things?
Yeah, they are. I would say they are three different things. So NP hard means everything you said is correct, but another way of sort of defining NP hard, which is equivalent to what you said, is a problem is NP hard if solving it in polynomial time implies that all of NP, any problem in NP can be solved in polynomial time. And so it turns out that an NP hard and a problem is also NP hard if and only if an NP complete problem can be reduced in polynomial time too. So think of NP hard as being like at least as hard as anything in NP. But to be in NP, you have to be a decision. And that's why your notes are saying that an NP hard problem does not have to be a decision problem. Now, this is all like very pedantic. I don't even like discussing these, idiosyncrasies of definitions. Like, conceptually, NP hard means at least as hard as anything in NP. NP complete means at least as hard as anything in NP, but also in NP yourself. And by hard, everything means like sort of up to polynomial time factors. We're just going to sort of ignore polynomial time blowups in runtime, meaning, n squared and n to the 10th are just going to be thought of as like, the same kind of runtime for purposes of the discussion. P space, any problem in NP is also in P space, but the reverse is not necessarily true. And that, I think that's maybe what you were getting at with, asking about my comment about P space being believed to be the vastly bigger complexity class than NP. Like 3SAT, pick your favorite NP complete problem, like 3SAT. Right? Like for 3SAT, it's believed that the fastest algorithm is roughly brute force, like try every possible assignment to the circuit and, evaluate the circuit on each of them, the formula, whatever, and see if it causes the formula to output true. That's a really slow algorithm, but it is in P space because, the amount of memory it needs is actually just linear in the size of the formula. So that's sort of indicating that P space, like even linear space, contains NP complete problems. So P space should sort of intuitively contain even harder problems.
One last rabbit hole to wander down. Cryptographers often say that if P equals P space, a lot of our trapdoor functions are broken. But my model of that is that it's something of an exaggeration, because like the algorithm to break our one-way functions, reducing it from like exponential time to some huge polynomial blow up, is still probably pretty bad. So is that mostly just like a complexity theorist saying that would be really gross, or is that an actual like security concern?
Yeah, I mean, you're totally right that, it could be that it's possible, we cannot rule out that P equals P space, but nonetheless, any algorithm for inverting like the one-way functions that we use today is totally impractical, despite its asymptotic complexity being polynomial in the size of the input. So, there are endless discussions of possible implications of this P equals P space is an even stronger situation, even crazier situation than P equals NP. That will raise this distinction, like, hey, P equals NP would be an asymptotic result. It doesn't necessarily mean there are practical algorithms for the NP complete problems. But, then there'll be follow-up counterpoints where people say, hey, like most of the natural problems that have polynomial time algorithms, actually, they do tend to be pretty practical. The polynomial tends to be, not a crazy one. It tends to be like at worst, like n cubed. It's all wild speculation. It's like saying if pigs could fly, what would the consequences be? Is that enough of an answer?
Yeah, I think so. Thank you.
Sure.
P space.
Yes. Okay. So are there questions about IP?
So does P space equals to NP times co-NP?
What is NP times co-NP? Like, do you mean the union of the two? Like each NP is a class of decision problems. Co-NP is a class of decision problems.
I saw so sharp set is NP complete, right?
No, it's NP hard. It's not a decision problem. Intuitively, it should be somewhat harder that like just at a rough intuitive level than an NP complete problem. The NP complete problem would be asking, is there one or more satisfying assignments? Whereas sharp set is saying, what is the exact number of satisfying assignments? Not just is it more than one or greater than or equal to one.
Because I've seen like quantifiers that satisfaction problems, and like someone wrote that P equals like for all universal quantifier, and co-NP is like extensional quantifier, and
yeah. So I think. Oh, sorry.
P space is like a mixture of both.
Yeah. So I think this is what you're getting at. So there is a P space complete problem, which is actually discussed very briefly in the book, but not much said about it, called TQBF. It stands for True Quantified Boolean Formula. Yeah, quantified refers to exactly what you're saying. These like there exists and for all stuff. So a TQBF instance is like, not only is there a Boolean formula phi as part of the input, but there's also like, it's asking like, does there exist a setting of variable x1 such that for all settings of variable x2, there exists a setting of variable x3 such that for all x4 and so on and so forth, phi is satisfied by x1, x2, x3, x4, and so on. That gives you a P-space complete problem. And as you add more quantifiers, meaning there exists and for all alternations, you sort of walk yourself from NP and co-NP up to P-space. So NP is just one existential quantifier. Does there exist, x values of x1 to xn that cause phi to evaluate to true? That's NP. That's an NP complete problem. Co-NP is saying for all x1, x2, xn, does phi evaluate to 0, to false? So that's a co-NP complete problem. And then as you add more and more alternations, you walk up something called the polynomial hierarchy, which captures there's a level for any constant number of alternations. And then P-space turns out to correspond to the situation when you have everything alternate. So if there are n input variables to phi, the P-space complete problem allows just an alternation every time. So, there exists an x1 such that for all x2, there exists an x3. So that's n alternations. And yeah, so I think that's conceptually how to think about the complexity classes sort of between NP, co-NP, and P-space is, every time you add another alternation from, there exists to for all, you sort of get a bigger and bigger complexity class. It's called the polynomial hierarchy, as long as there's only a constant number of alternations. And if you take the number of alternations all the way out to n, the number of input variables, you then get a P-space complete problem, which is believed to be, sort of much harder, if you will, than just NP or co-NP itself, which just each of which just has a single, no alternation, just one quantifier. Did that make sense?
Okay, I will just process that.
All right, I get one more sentence. I guess you might then ask, like, where does sharpsat live in there? And the answer is, I mean, it's because it's not a decision problem the way, TQBF and SAT and unsat are, it's not directly comparable. But, with sharpsat, there are no alternations. There just is count. You're sort of taking the existential quantifier of NP and replace it with like an exact count instead of a inequality, greater than or equal to 1 satisfying assignment. So I'd say conceptually, I mean, there's something called Toto's theorem in complexity theory, which kind of relates like sharpsat to NP-like complexity classes, but this is way in the weeds. So I would just think of sharpsat as sort of living somewhere in between the NP complete problem of SAT and the P-space complete problem of TQBF, somewhere in between.
Is there an example of a problem that's beyond P-space? Except I know there are unsolvable problems like ping problems, but are there just other examples of problems beyond P-space?
Yeah, there are. And I have two answers to that. So one is there are things called the time and space hierarchy theorems, which kind of say that whenever you add extra time or extra space, you can solve more problems in a sense. And actually, I want to be careful by not embarrassing myself. I only remember off the top of my head the time hierarchy theorem, which says, if you take any runtime t and you allow like an extra logarithmic factor of time, sort of, there will be at least like one more, there are some more problems you can solve in that time bound that you couldn't solve in the previous time bound. But these problems are like very artificial. This is proved through something called a diagonalization argument, something complexity theorists like that have really nothing to do with any practical proof, anything. So my other answer for you is actually I'd say the most natural class that is probably bigger than P-space, although, we don't have definitive answers to any of these questions about how these classes relate to each other, would be NEXP. So that's non-deterministic exponential time. That is like the exponential time version of NP. And in fact, there's a famous result on probabilistic proof systems called MIP equals NEXP, which is actually discussed in the book. And that says that any problem solvable in non-deterministic exponential time is also solvable by a two-prover interactive proof. We haven't talked yet what that means, but we cover it in chapter, it might be 8 now, I forget. Two-prover interactive proof with the polynomial time verifier. So that is a natural complexity class NEXP that people think is bigger than P-space. So IP, that's one prover interactive proofs with polynomial time verifier, that captures P-space. That's a highly non-trivial result that they're the same class. And MIP, where you add a second prover, that captures NEXP. That's also a highly non-trivial result. So intuitively, like adding the second prover is believed to buy you a lot more power. And indeed, we'll see, like even in the practical context of snarks derive from multi-prover interactive proofs, in some sense have nicer properties. They don't strictly dominate ones derived from one prover interactive proofs, but they have some nice properties that the snarks derived from one prover interactive proofs do not have. So basically, anytime we consider an information theoretic model in this book, whether it's one prover interactive proofs, two prover interactive proofs, PCPs, IOPs, there are two kinds of results people will have proved about that. There will be what are called the scaled up results, where they're interested in a polynomial time verifier, and those proof systems capture huge classes of very hard problems, P-space, NEXP, and so forth, because polynomial time verifiers, can solve super hard problems. That's not requiring the prover to be polynomial time, right? Only the verifier. So these proof systems can solve super hard problems, but they're not useful in practice because no one can solve those super hard problems in the real world. So the snarks people use, they're kind of scaled down versions of the same kinds of results where we insist that the verifier be linear time instead of polynomial time. And then you wind up, rather than solving like P-space complete problems or NEXP complete problems, we wind up solving NP complete problems like circuit satisfiability. And yeah, so when we get to snarks, which, shouldn't be that long from now, we need to sort of get to the cryptography, but we'll be focusing on these NP complete problems like circuit sat, but, there'll be like analogs of the results with polynomial time verifiers where the class of problems being solved are massive, and they go even beyond P-space to NEXP. Okay, so thanks for letting me just ramble about this stuff. Ideal membership is X space. Okay, I didn't know that. So apparently exponential space has a natural problem for mathematics in it.
In the book, like the space like O n to the 3C, it's just a generic one, right? So it's just an example.
Yeah, so there's it. So the result IP equals P space, right, has two directions. Like you have to prove two things to show that IP equals P space. So to repeat what IP equals P space means, let me do that just to make sure everyone's on the same page about what we're talking about. So IP is the class of all languages solvable by interactive proofs with a polynomial time verifier. The prover, of course, could be exponential time. And P space is the class of all problems solvable by a polynomial space algorithm. So there's no notion of a prover here, baked into the definition. They turn out to be the same class of problems. And so to show that, you have to show two things. So one is for any language in P space, you have to give an interactive proof for it with a polynomial time verifier. And that's called the hard direction of IP equals P space because, like the people who proved that had to develop these super awesome protocols like the Sumcheck protocol and these notions of arithmetization that we talked about today, like really breakthrough transformational protocols. The easy direction is the other one that is showing that any problem with an interactive proof with the polynomial time verifier is solvable by an algorithm that uses polynomial space and no prover. And so the way that's shown, it's an actual transformation where you sort of take the verifier in the interactive proof that you're assuming exists for your problem and sort of use it to give a polynomial space algorithm for it. And so if roughly speaking, if the verifier runs in time n to the C in the interactive proof, and you sort of walk through this transformation of that verifier into a polynomial space algorithm for the problem, and I didn't really discuss much at all about that transformation in the book. The space bound of the resulting algorithm, I'm pretty sure it's actually n to the 2C. So basically, however much time the verifier uses in the interactive proof, I think the space complexity of the algorithm that comes out with no prover is the square of that time bound. But I don't know for sure off the top of my head, and I definitely put the number 3 in the book just to make sure I didn't say anything, slightly too aggressive. So yeah, I mean, it's a generic statement that you take any interactive proof with the verifier running in time n to the C, think of C as 3 or 4 or 10, and it turns out you can turn that into an algorithm with no prover, and the space usage of the algorithm will be like the square or the cube of that time bound of the verifier. Does that make sense?
Yes. The next question is about IPs in P space. The first thing we need to prove, because I will just read it. So optimal word strategy can be computed in space, blah, blah, blah. So this, I didn't find the source. It's like lecture 17 in, I think, 2006 lecture. I didn't find it, but I find another source. So the proof is done by induction, right? So if it's the same, I won't lose.
Yeah. I think there's a natural way to do this. I think there's basically just one way to do it. So your source that you found is probably just fine. And actually, if you wouldn't mind sharing that source with me, I can then add it as an alternative reference since apparently it's not easy to pull up this book unless you, I don't know, I guess have to order it or something. So it'd be good to have a second reference. This is sort of considered like a folklore result almost. So I wasn't sure what a good exposition of it would be. And I know that what I pointed to has a nice, like lecture note style exposition. So if you found another one, I'll add a pointer to it. That'd be helpful.
Okay. And I think just one last question. The proof just proved that I think the interaction between the proof, so the time and the space required for. So we don't count the space required for the prover to actually solve the problem, right? So
what's going on is we're assuming the verifier runs in polynomial time. We're not directly assuming anything about the prover, but it turns out that an optimal prover strategy itself can be computed in polynomial space. So you could think of you could think of a prover that it turns out like that the prover might you can imagine the prover doesn't actually know how to solve the problem that the verifier is interested in, if you will, in the interactive proof. All it knows is what the verifier did, like the verifier's computer code, sort of. And just by assuming that the verifier is in polynomial time, it can actually figure out whether or not there's any way to convince the verifier to accept with non-negligible probability in polynomial space. So like what that means is, by assuming that there is an interactive proof for the problem with a polynomial time verifier, you're sort of directly giving a problem, an algorithm in p-space for the problem, even if you didn't a priori know an algorithm in p-space for the problem, right? So the algorithm in p-space for the problem literally just like computes an optimal prover strategy to try to convince the verifier to accept. And if that probability turns out to be like more than a third, then the input must be in the language, because any interactive proof for the language, by definition, yes inputs have to result in acceptance probability at least 2/3, and no inputs have to result in acceptance probability of the verifier in most 1/3. Does that make sense?
So the prover try to prove the answer of a problem to the verifier. I mean, the process of a prover computing the answer doesn't count. But it's just
so what I'm trying to say is there is a way to figure out what the optimal prover would do in polynomial space. So like there might be some cheating provers who take infinite time trying to trick the verifier, okay? But they can't do better than what the optimal prover strategy would do by definition of the optimal prover strategy. And that optimal prover strategy can always be computed in polynomial space. Given a description of the verification procedure, which by assumption runs in polynomial time, right? It turns out it's possible to figure out what is the optimal prover strategy with polynomial space. So while there are cheating provers that, like the cheating prover in any interactive proof is allowed to spend infinite amount of time trying to, figure out the best thing to do, there's no reason for the cheating prover to spend more than polynomial space. Does that make sense?
Yes. So the strategy and the probability, the strategy of the prover used to convince a verifier, and the acceptance probability of the prover and the acceptance probability of the verifier can be computed in p-space. So I know, I understand this is the case, but I mean the answer to the actual problem. Maybe I'm understanding this wrong.
So yeah, I mean, just to summarize, I guess in one sentence, the p-space algorithm, the claim that you could any problem in IP is also in p-space. The p-space algorithm, the way it works, for the problem that's assumed to have an interactive proof with the polynomial time verifier, the way it works is it literally just figures out what the optimal prover strategy would do, like how it would respond to every possible challenge the verifier might send it. Right. And then moreover, figures out what the verifier's acceptance probability would be when interacting with that optimal prover. And it turns out all of that can be done in polynomial.
Sorry if this take too much time, but
people can just drop off. If someone has another question they want to add, they should interrupt. But otherwise, we can talk. I do have to go and add one. But I'm happy just to keep chatting for the remaining 8 minutes. I guess one thing I do want to clarify to anyone listening is what we're discussing here has essentially no further relevance to the book. This result is discussed sort of for context and just like sort of historical knowledge. Like it's good to know that, like you cannot hope to give an interactive proof with very low communication, very, very fast verifier for problems that live like even beyond p-space, right? But we're never going to refer back to this result again, really, especially this direction of the result, which says, because this direction of the result is about limitations of interactive proofs. Whereas the book is about how great and powerful interactive proofs are and how we can use them to give amazing cryptographic protocols that we all want to deploy in like the blockchain or something. So it was important to describe the result, and it's great to have this long discussion about it. But, if you don't understand any of this, it's not going to matter. Just want to make that clear. Okay, my wife is telling me I have 3 more minutes rather than 7. So anyway,
I have a good question about the book. Can I ask?
Yeah, please. Thanks.
Very fast. So what I wanted to bring up, the Sumcheck, we discussed it last time, that doesn't need to be linear and is in the book. So the one that we are implementing is not linear and is that one that is exponential, right? There is no escape from that exponential evaluation, right?
For Sharp's hat?
No. For the exercise that we did last week, you have to evaluate it. The prover have to evaluate it in exponential time, right?
Yeah. Well, so, exponential in what? So the goal of the Sumcheck, the point of the Sumcheck protocol is to sum up the polynomials evaluations over the Boolean hypercube. So if so that's 2 to the v values, where v is the number of variables. So there's no avoiding exponential in v time. But then when we go and actually apply the Sumcheck protocol to specific problems, it's often the case that v is only logarithmic in the real input size. So exponential in v is actually polynomial in like the real input size. Does that make sense?
Yes. So it was clear that we need to do it exponentially when we implement. But then it could be the input not be exponential. The other small question I have is that in page, I guess my page, but when you describe the SAT problem, you say size S, but n variable. What is size there?
Yeah, I hate this. I know this is a source of confusion. So basically, this is why I didn't describe a formula as like a binary tree. So the way I'm thinking of it is n is the number of input variables, but you can, the formula, think of it as a binary tree, which can have which has S leaves, okay, where S might be much bigger than n. But then each leaf is like some copy of an input variable. So it might be that, there's, a billion leaves, only 100 input variables. And then, so like each input variable is like repeated, a billion over 100 times. Yeah, as you read out the leaves, if that makes sense.
Because you need to use them in different gates.
Right. So I have to find a way to make that clearer. So maybe I just need to say the formula is a binary tree, which has S leaves. Each leaf is like, a copy of one of the n input variables. I guess that's going to be the best way to say it. So I probably have to make those edits, which will be annoying to make, unfortunately. But yeah, so thanks for the question, since it's confusing.
Thank you very much. Okay, I feel like I had stuff.
Okay. Well, thanks everyone. And yeah, I got to run too. I appreciate all your patience and your time and listening. And yeah, I will see you next week. And we'll talk about the reading's going to be the GKR protocol in the final section of chapter 4, but it'll all be discussed, I think, in the chat by Thor. So yeah, thanks for sticking around this whole time. See you next week.
Thank you.
Thank you. Bye.